and welcome to the course Design Bore Fields with Confidence. In this third chapter of the second part, we will again talk about bore field physics, but now not about the short-term effects, which we discussed last chapter where we introduced the effective borehole thermal resistance, but today we will be talking about seasonal and long-term effects, namely the variation of the borehole wall temperature. Because last time, just to recap, what we said is, well, if we have this temperature profile and we see different things, we see seasonal variation, a long-term temperature drift, but we also see different temperatures. And we said that this effective borehole wall temperature we introduced last chapter basically determined the relationship between our borehole wall temperature, or ground temperature, and our fluid temperature, which we're actually interested in. Now, on the short time scale, the borehole wall temperature does not change, and it's just the fluid temperature that varies. But of course, over the months, over seasons, over years, this borehole wall temperature will change, because the ground is a little bit like a battery, and it can be charged and it can be discharged. And that's exactly the long-term and the seasonal variation you see on our temperature profiles, and that's what we will be discussing today. Now, if you talk about bore field physics, and if you think about it, it's actually a really complicated problem. Because, to start, it's three-dimensional. Right? It's a volume, basically, in the ground. It's transient, because it changes over time. And it's a heat diffusion equation. So it's a really complicated mathematical problem. Because conceptually, in a bore field, there are different boreholes, and they all interact with each other. So that's one complexity. And the other thing is that the ground does not stop at the edge of the bore field. It continues. So there is also this interaction with the concept of the infinite ground. And in order to make this, or to visualize this and to understand this, Eskilsson, in his PhD dissertation in 1987, conceptualized this as G-functions, which are ground response functions. And you can think about these functions as an answer to the question, how does our borehole wall temperature, so the temperature at the interface between our bore field and our ground, how does this borehole wall temperature evolve under a constant load? So what we try to conceptualize is we have a bore field, and every bore field, every configuration, every depth, every geology has its own unique fingerprint, its unique G-function. And what we need to think about is if we have this bore field and we inject a constant power into it, let's say 1 kilowatt, how will the system react? And of course, as you can see here on the slide, if we inject heat into it, the ground heats up. And in the beginning, it heats up faster. So that's because the heat we inject into the ground gets trapped, let's say. It's physically not 100% correct, but it's insightful. It gets trapped around the borehole, and the more heat you inject, the warmer your borehole gets. But on the other hand, the heat also dissipates away because of the conductivity of your ground. And the longer you inject this heat, the more heat gets dissipated, and basically your circle of influence around your borehole, it increases. So you need more energy being injected into the ground to increase your temperature. And that's why this line is not linear. It goes steep up and then it flattens off. So basically, if we keep injecting the same power into our system, it will increase in temperature, but increasingly slowly, let's say. So the longer you do this, the longer you have to wait to see a certain effect. So that's this slope. Now, you can, of course, see it's already in days, but over months and years, this effect is even way more pronounced. And we have an influence on this G-functions as a geothermal design. Because, of course, if we place our boreholes closer together, we can understand that the interaction between the different boreholes will also be more pronounced. And this you can see on the figure to the left of you. Here you see a bore field where we have spacings between the different boreholes of 8 and 6 and 10 meters. And what we see here is that the boreholes that are the furthest apart, the 10 meters, the G function is actually the lowest. So this means that if you inject, extract, it's the same, a constant amount of power in or from the ground, this bore field with the boreholes spaced the furthest will actually have the lowest effect of it. And that the G function is the lowest, so the effect on the long term is actually lower. Well, and of course this can be understood since the boreholes are further, so their interaction is less. But what is interesting is that if you go to short time scales, we go back to days, for example, you see that all spacings overlap. And they all go down the same way. And that is because, as I talked about, this region of thermal influence, let's say, in the beginning, if we do this 2 days, 3 days, the boreholes do not feel each other. They do not yet interact. The heat is trapped around the different boreholes, and it takes a couple of months before one borehole notices the other. So it takes a couple of months before these regions of influence around each different borehole, they actually interact with each other. And once they interact, the ground heats up, or the borehole wall temperature heats up more significantly. And that's what you can see in this graph. So we have the blue line from 6 meters borehole spacing. These boreholes notice each other a little bit sooner than 8 and 10 meter spacing. So this line deviates faster because there is interaction already somewhat sooner. And then we have our 8 meters deviating from our 10 meters as well. So that's for borehole spacing. Now, the same reasoning you can do for borehole configuration. So imagine you have 9 boreholes and you need to place them. Well, you can do that either in a grid of 3 by 3, or you can place them all on a line. And as you can see here, if you place them all on a line, also our G function will be lower, meaning the effect of the imbalance will be less. And this is due because instead of having the thermal interaction between all the boreholes, here we have more interaction with the infinite ground. If our boreholes are packed densely together, the borehole in the middle, it cannot exchange its heat with the surroundings. So this bore field in total will heat up sooner. Now, if we have all our boreholes on the line, it's way easier for all the boreholes to exchange heat with the undisturbed ground, or with the infinite ground around it. So that's also why if we place them on a line, the G function and the long-term effect, and hence also the influence of the imbalance, will be less pronounced. Now the third parameter, which we already talked about in the last part, is the ground conductivity. Now typically you do not have an influence on this. It is what it is, the geology at a certain project location. But for example, what you can do as a designer, if you know that there is a bed conducting, thermally conducting layer at a certain depth, is that you decide to not drill in that layer. So you pick your desired borehole depth, borehole length in such a way that you keep a very good average ground thermal conductivity in order to again have a better G function. So these are all concepts that are important when talking about G functions. Now, we talked about these G functions as well. They are all constant and constant power injection. And of course, if we extract power, the figure is the same, but it's just flipped, and the ground cools down year after year, but always less. But our load, in reality, it's not constant. It varies from month to month, but in reality also from hour to hour to hour. So how can we go from this constant behavior towards a seasonal and a yearly behavior? And that's what's called temporal superposition. Now, this is a little bit a complicated concept, perhaps, but what we do is we take our loads, here given to the left, and we will divide it based on the time steps. So imagine it's an hourly load and we need 1 kilowatt the first hour, or from hour 0 to 20, and then we need a half, and then minus a half, and so forth. So we divide it into separate steps. And what we then do in the second image is we will assume that each step is constant. So what do I mean by that? Well, you see that in the beginning at time step 0, we need 1 kilowatt. So what we do is we say, okay, at time 0, there is a constant load of 1 kilowatt forever. That's the dotted line. Now at time step 20, in this case, we need half a kilowatt. But we already have this constant 1 kilowatt. So what we will do is we will say, okay, at time 20, which is the striped line, let's say, there is a constant load of minus a half that starts. And that also goes on forever. So this means that if we sum all the lines at time step 20 or 30 and so forth, we have plus 1 kilowatt minus half a kilowatt. So in total we have again our half kilowatt of power. Now at time step 40, again we now have minus 0.5 kilowatts, and we already have now a constant load of plus 1, of minus 1, and we need to go to minus a half. So what we do is we will again start a constant load now at minus 1, so that when we need now calculate our resulting load between 40 and 60 as a time step, we have plus 1, minus a half, minus 1, so we have in the end our desired minus a half. And this we do for every pulse in our load. If it's hourly, we will do this 8,760 times per year of the simulation. And this is what's called load decomposition. So we decompose our load profile into constant time steps. Now, why do we care about these time steps? Well, it's because we know our G functions for every constant load. So for a load of 1 kilowatt, we know, okay, this is how our G function behaves. For a load of minus a half, yeah, it's the same G function, but now negative and scaled by minus a half. And this we do for every constant load of the second figure. And then we end up with the graph on the right, where you see that at time step 0, there is this dotted line going up, which is the G function of our first constant load of 1 kilowatt. At time step 20, there is our striped line going down, which is our G function multiplied by minus a half. And then we have our G function multiplied by minus 1 and so forth. And our resulting profile is now just the sum of, again, all these G functions at all these different steps. And that's the bold line you can see on this graph. And by doing so, we can use this simple concept of our ground response functions, the G functions, how we can influence them, and basically use this temporal superposition of all the different loads at all the different times to end up with a resulting seasonal and yearly variation of our wall temperature. Now, I just want to make a couple of remarks with regards to these G functions. It's assumed that all heat transfer is purely conductive. This means that everything related to groundwater flow is not explicitly taken into account. Now, if you have groundwater flow, and as said, the ground is a little bit a battery, so it heats up and it cools down. But if water flows through, yeah, part of the heat is taken away. And then you see this typical graphs like the one here on the slide, these temperature plumes, where you see that the influence is no longer symmetrical, but it's moved due to the groundwater flow. Now, groundwater flow can be beneficial for your case if you have quite a large imbalance. Having water flowing away, it's actually a good thing. If you want to use your bore field really as a storage of heat, yeah, you don't want this groundwater flow. And depending on if it's beneficial or not in your case, what you will do is you will try to arrange your boreholes in such a way that you have more or less influence of the groundwater flow. So if you want your imbalance to go away, what you do is you place all your boreholes perpendicular to the flow so most of the heat can get away. If you want to keep everything as close as possible, pack your borehole really dense and orient it in such a way that the influence of the groundwater flow is minimal. Now, perhaps you now say, well, this groundwater, how do I know it? Where can I find information for it? And that's exactly the problem. It's really complicated to take this into account. Perhaps you have to do measurements and so forth. And you also need very detailed numerical simulation tools like Sequent or ModFlow or FreeFlow to take this into account. So if you have a very complicated project where it really is important to know exactly how your geothermal system will behave, you need more advanced software packages. They're all linked in the textbook, no worries. But for most design practices, assuming it's purely conductive is actually very good and it's a good way to move forward. A second remark is that the concept of G-functions can also be used to calculate the interaction between different systems. So I have a geothermal system and my neighbor has one. We can use the concept of G-functions to calculate the interaction between the different systems, which is then called cross G-functions. And this is the problem of thermal interference, which we will cover on later in this course. So to summarize, when we're talking about the long-term effects, we talk about the ground temperature changes, and this is basically an energy problem. Now, if you recall, the short-term effects, that was a power problem with the effective borehole thermal resistance. Now we have an energy problem. If we extract more heat from the ground than we inject in it, our G-functions will make sure that our ground goes down year after year. And the good thing is that we can influence these G-functions depending on your borehole spacing, your configuration, and your ground conductivity, which, as we said, you cannot change, but you can decide which layers you want to work with. So now, as a conclusion, we basically covered all the borehole physics basics. Over on the textbooks, you have more mathematical detail. You have also, related to G-functions, some more different models, how you can calculate it. So it's over there in Deepening Insights if you have interest in that. But I hope you now understand what's behind these profiles. You see here what we discussed today, this downward going trend. You clearly see here the G-function because it goes down steeper in the beginning and over the years it flattens out. And you also see the effective borehole thermal resistance as being the difference or important factor when it comes down to calculating the difference between the borehole wall temperature and fluid temperature. Now that we know this, let's jump into GHE2 in the next chapter and actually design our first geothermal system together to really understand how these profiles work and what we can learn from it.